Hello? Ah, yes, now. So I think we should start. Reiko? Like with students. Silence, please. So it's my pleasure to introduce Patricia Metidieri, who is going to tell us about, I suppose, its work based on your PhD thesis, which you defended recently at Radboud University on the wonderful, fascinating world of entanglement in quantum entanglement in curved space-time. So very frightening words: entanglement, curved space-time, quantum, and you're going to put all that together for us. So the floor is for you. Thank you.
Okay, so I hope you can hear me. Please let me know if that's not the case. And first of all, let me thank the organizers for giving me the opportunity to present my work in this wonderful meeting. It is an absolute pleasure to be with all of you. And yes, I will try to change gears a little bit and tell you something about, well, the world of relativistic quantum information, or more concretely, what is this entanglement in quantum fields? So I'm aware that, perhaps the audience is very mixed. Not all of us are in the same page. I find talks that are completely outside my comfort zone. So what I'm going to try to do is to account for that and give you a very broad motivation, which hopefully will be, with some things that you already know. Then I will give you some small technical details, still very non-technical, of the kind of framework I work on. And then I will share with you two applications that I think are really nice, at least from a physical point of view. Finally, I will summarize this work and give you some conclusions. So let me start motivating this talk by, talking about something absolutely boring, perhaps something that you all in this room are familiar with. That is correlations. So essentially, if I show you some plot like this, I tell you you have two random variables, and you see something like this, you will think, yeah, this seems like to be correlated. Something like this, you would say, me, perhaps not so much. And we are all familiar, or we all know many examples of correlations in mathematics and also in physical systems. It also appeared in some talk yesterday. We know that the motion of two coupled harmonic oscillators are also correlated, the position of two harmonic oscillators, right? But if I ask you, all of you, to just try to come with a very simple example of correlations, most likely you will come up with an example that is of the everyday world that we see around us, right? And today I want to go a little bit beyond that and tell you about a very special type of correlation that goes a little bit beyond that world. So essentially, you all know that, well, while our everyday world behaves in a very nice way, so we have classical mechanics, where we have our nice trajectories, we have a deterministic world, and we have all these correlations we know. If we zoom into the smaller scales, then our world behaves as a quantum theory. And then we don't have notions of trajectories anymore. We have an uncertainty principle. The quantum theory is probabilistic, but most importantly for this talk, we have other notions or new notions of correlations. And in particular, I want you to think of entanglement, which is the main topic of this talk, precisely as a type of correlation that exists in quantum systems and that has no classical counterpart. Now, yeah, probably I see some bored faces like, okay, yeah, correlations, whatever, why is this important? Why do we even care about entanglement? Well, don't take it from me. At least, I can go to one of the fathers of quantum mechanics and say, well, maybe you should care about entanglement because actually, according to Schrödinger, it's not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure of classical thought. Very well, this is very philosophical. Probably most of you still don't care. No problem. I'm with you, but I'm a physicist, so perhaps I want to ask the question, why should we care about this? Is there practical applications why we should care about entanglement? And I can give you at least two reasons. First of all, it's very much a resource used in quantum technologies. In fact, it is the resource that allows for quantum computation to be more advantageous than its classical counterpart, in the sense that some quantum algorithms well, that we can have quantum supremacy, if you've heard of the word. It's also an important resource in, for example, protocols of quantum key distribution. You might have heard of this, or even in the most, something that I find mind-blowing, such as quantum teleportation that allows you to teleport the information of a state from one point to the other, just because of this resource, entanglement. But it's not only something practical. I mean, for many mathematicians in the room, probably you are just looking at this and thinking, okay, why do we care? But you know, this is also important in fundamental physics. Okay, perhaps you still don't care, but at least I do. And one of the reasons is, for example, we think that this entanglement might help us understand some aspects of black hole information loss paradox. And in particular, it might also help us to understand what are the quantum signals from the early universe that we might or might not be able to see. And I'm going to focus more on this part of the talk. And in order to do that, I have bad news for you. And it's that we cannot typically, stay in the nice setup of quantum mechanics where, we have finite degrees of freedom, things work nicely. We have Hilbert spaces that work very nicely, that are nice and relatively simple. As, again, saying relatively, this is already quite a complicated word. But we have to go to quantum field theory in core spacetimes, at least for this last application that I want to talk about. So when we want to study correlations and entanglement in quantum fields, we immediately find some surprises. The first surprise, for example, is the following. So consider a quantum field in the vacuum state, which I'm representing here with a kind of a quantum noise. So you know that the vacuum state of a quantum field is something more interesting than just empty space. Now choose 2 points, 2 space-like separated points, which thanks to yesterday's talks, I don't have to tell you what they are, of this quantum field. So since they are space-like separated, no signal can travel between these 2 points of the quantum field. But now you are up for a surprise, because if you compute the 2-point correlation function, vacuum correlation function, you are going to find that it's non-zero. So there are correlations in the vacuum state of a quantum field. So even more surprising, you realize very quickly that it's not only that the vacuum state is correlated at space-like separations, but these correlations contain entanglement, this fundamental resource that I want to talk about. So yes, you go into this and find out that actually entanglement is built into the very structure of the vacuum in quantum field theories. Now I'm just putting this kind of take-home message for the first part of the talk, but there is a nice and beautiful result that will tell you about this, that is called the Rejzner theorem. Now, it's not important that I tell you at this point what this theorem is about, but its implications. I can tell you about this thing after the talk. And the important point here is that this implies that the vacuum is so entangled that by acting on it with local operations, we can essentially approximate any global state in the Hilbert space of our theory. Now, believe me, this is quite mind-blowing. But as a physicist, now you start thinking like, yes, this is everything I was waiting for. I can exploit all this resource. There's a lot of it. Even if in quantum mechanics there is not so much of it, there must be a lot. But now the point is, how much? And where is it? And those 2 questions, which are apparently very simple, turn out to be very, very hard to answer. So just to give a little bit more of context, imagine that we have 2 causal space-like separated compact regions, and I want to describe how much entanglement is there between all degrees of freedom of a field that are compactly supported here and those that are compactly supported here, where this is a Cauchy hypersurface that Angrid told us yesterday about. And turns out that this is really, really hard. There are, in fact, I think there is no answer for such a problem. There are different approaches that you can use. And I'm not going to try to tell you about all of these approaches. My objective here is much more humble. I'm just going to tell you about one possibility or one possible approach to analyzing or to try to answer part of these questions, so to analyzing entanglement in quantum field theories. That is based on this wonderful review by Bianchi and Sachs that you can see is quite recent, by work of Martin and Menim, and also by some work that I did during my PhD. Very well, so the physical picture that you have to have in your mind for the approach I'm going to tell you about is that, well, part of the complication of why trying to understand entanglement in quantum fields is so complicated is because these are complicated objects mathematically. For the experts in the room, they are described by type 3 von Neumann algebras. They host infinitely many degrees of freedom. They bring a lot of complications. But the point here is that even if quantum fields host infinitely many degrees of freedom, we cannot access them. We are limited by experiments. We are limited by our capacity to simply probe quantum fields, right? So for example, essentially, even if a quantum field is very complicated, we are going to test it or probe it with a given detector that is made of finite pixels. We are measuring at a finite energy, and our pixels have a finite resolution. So at most, what we are finding of the quantum field is kind of a smeared version. And we have finally many degrees of freedom. So now what I'm going to do, or what the framework that I'm going to describe is about, is precisely taking this point of view, plus one additional simplification, which is the Gaussian formalism, which means I'm going to consider only Gaussian states and free evolution, and, well, yes, this truncation of degrees of freedom based on this physical motivation. If you put these two things together, then you find that you have a framework with nice features. In particular, you avoid ultraviolet divergences that you typically find in quantum field theory, because again, you have reduced your problem to working with type 1 von Neumann algebras, handling a number of degrees of freedom. You avoid ultraviolet divergences. Moreover, since we're working with Gaussian states, it turns out that we can compute reduced states. And these reduced states are also Gaussian, which means, as I will explain later, that they are very simple and we can characterize them geometrically. Additionally, we can use results from quantum information because, again, the mathematical structures we have in this framework are those of quantum mechanics. We can import many of the techniques that are used and well understood in quantum information. At this point, you must be thinking like, this is too simple. I would agree with you. But well, the nice thing of this framework, and this is why I'm trying to sell it to you, is that you still retain some features of the full quantum field theory. In particular, it turns out that every reduced state or general reduced states that you compute using these techniques are mixed. And this is a consequence of this great amount of correlations and entanglement that you have in the vacuum of a QFT. Now, yes, this is still very simple. Again, I'm just going to do very simple things in this talk. I'm sorry, I cannot do complicated things. So the point here is that, yeah, of course, this is so simple that it has to have limitations. And of course, it has them. Actually, every approach that I know of analyzing entanglement has some sort of limitations. Either, they are technical limitations or, well, we are limited by what we can observe. So in this case, the limitations are obviously that, well, we are limited to free theories and Gaussian states by construction. Now, yeah, this is a big limitation, but I'm going to argue we still have physically interesting situations with this setup. In particular, I'm going to talk about quantum field theory in the early universe as one of them, and other applications that are closely related to experiments. So, I'm happy to live with this. The problem of this approach is this second limitation. This one is a bit more concerning, and is that I'm focusing on a finite subset of degrees of freedom when a quantum field hosts infinitely many of them. So how do I know that whatever results I obtain for a given subset of degrees of freedom are general? Or, they don't depend on the choice, the concrete choice of degrees of freedom I decided. Well, yeah, this is concerning. But in order to palliate or to alleviate this situation, this is what I'm going to try to convince you that, well, you can do this if you try to focus on universal properties of finite subsets of degrees of freedom. So properties that do not depend on the particular choice of degrees of freedom. And this is something that you can do in certain situations. This is what I want to talk about. Yeah, so this is what I'm going to try to do in the rest of the talk. Sorry, if at some point the microphone goes out, you don't hear me, please stop me. Okay, and this leads me to the second point or the second goal of this talk, which is essentially to discuss two interesting applications, at least two interesting applications for physics. And these are based in these works. Some of them I'm participating and in collaboration with wonderful people, Aguyo Bonga, who are my PhD advisors, and also some other amazing collaborators that you can see here. So let me start now with the boring part of the talk. Since the audience is quite mixed, I also wanted to give a bit of a flavor of what are the nice mathematical structures of the formalism I'm working on. I hope that I succeed and that you don't fall asleep by the end of this section, but if you do, please wake up for the applications. I promise you that they will be worth listening to. So let's consider the physical setup, and for that I'm going to consider a manifold, well, a space-time, that is globally hyperbolic, as Angret told us about yesterday, which means basically I can foliate it with Cauchy hypersurfaces, which luckily I don't have to discuss because Angret did the dirty job for me. Now, I'm also going to consider natural units, which physicists love. Sorry for the rest. And I'm going to consider a free quantum scalar field in the canonical formulation, which essentially means I'm representing it with two operator value distributions, the field and the conjugate momentum, that is propagating as a set on a globally hyperbolic spacetime. Now, the fact that this is a free quantum scalar field is important. And also that is on a globally hyperbolic spacetime because, as it was mentioned yesterday, global hyperbolicity ensures that the Klein-Gordon equation in this spacetime is well posed as an initial value problem. Moreover, the fact that the quantum field is free ensures that the phase space has the structure of a vector space, which means I can identify its tangent space with itself, and then the symplectic form on this phase space can be seen as acting on the phase space itself. And this is something that if you've opened a textbook, physics textbook of quantum field theory, you've seen many times. This is initial data, elements of the phase space consisting of two functions, and this is how the symplectic form would act in this initial data, which I'm considering to be of compact support. Now, it's usually convenient, and I'm going to find it convenient to define the Klein-Gordon product, which is simply a complexified version of this. There are some more technical details in this, which I'm going to completely ignore for the moment. But anyway, so this is how I'm defining the Klein-Gordon product. Very well. So next, I'm going to introduce some useful notation. This is just notation, which essentially is a convenient way of organizing linear operators. As I mentioned earlier, phi and pi are not operators of your Hilbert space, they are operator value distributions. If you want to obtain operators in your Hilbert space, you have to smear them out. And in this case, what I'm doing is I'm identifying, let's say, these smearing functions that we are using to average these operator value distributions with initial data of compact support. And then I'm writing this using the Klein-Gordon product that I introduced in the previous slide. Very well. Then what I will be describing as a local or a single mode of our system is essentially the algebra generated by two such smeared operators such that they are non-commuting. So far, so good. Now, you must be thinking, why are you complicating your life so much? We are happy with just, finding some smearing functions, smearing things, and we are happy with it. And I agree. But the thing is, this brings some clarity when it comes to talking and identifying subsystems. In particular, for some of us, well, we are used to talking about quantum subsystems as subalgebras of observables. And for those of you who are working in classical mechanics, well, for these linear systems, you would say, yeah, that the classical subsystem can be, or is identified with a symplectic subspace. But now, this identification allows me to basically talk interchangeably of these two. So we'll talk about quantum subsystems in a language that is, and I will show, is easier and convenient. So the language of symplectic geometry. And in particular, what this is also specifying, which is important, is, even though in many books of quantum mechanics, this is not evident, entanglement is not a property of a quantum state alone. It's a property of a quantum state and a choice of subsystem. But again, this subsystem is identified with some symplectic subspace, not with the basis that we use to define this subspace. And this will be important later on. Anyway, as I mentioned earlier, for physical reasons, I'm going to focus on finite dimensional subsystems, which means that these symplectic subsystems A are going to be finite dimensional. Very well. So I need the second ingredient I mentioned in my framework is that of Gaussian states, which are essentially the simplest states that you can consider, and that, as you know, can be fully characterized by their first and second moments. In this geometric language, I would say that, well, this first moment defines a covector in your phase space, and the second moment can be split into an antisymmetric part and a symmetric part. This is the Klein-Gordon product, is fixed by the symplectic structure, but this part depends on your quantum state. And this is what is called the covariance matrix and defines a two-covariant tensor in your phase space. Now, since these states are Gaussian, higher correlations follow from Bick's theorem. But now, I want to bring your attention to something that I think is quite nice, and is the geometric structure of these simple systems. And that is that for pure Gaussian states, we can define a linear map in phase space by taking the inverse of the symplectic form, which in the context that I'm defining exists for a compatible metric in phase space. And then what we find is that J defines a complex structure. So basically, its application on elements twice gives you minus the identity for pure Gaussian states, as I mentioned. And this makes this trio a Kähler space. So there is a Kähler, these Gaussian states and systems can be described in terms of Kähler geometry, as was pointed out in, for example, this recent review. We can also describe mixed Gaussian states in this language. But in this case, instead of having a Kähler structure, well, a complex structure, what we have is something else. We have what these people call a restricted complex structure, which means that this linear map, you act twice and gives you something that is strictly smaller than minus the identity. Now, why do I mention this? This is, perhaps a bit abstract. Why is it interesting? Two reasons. First off, this kind of geometric language allows you to treat not only bosonic systems, that's what I'm describing, but also pre-fermionic systems in Gaussian states with the same language. It's just Kähler spaces. But second, and most importantly for this talk, is because the spectrum of J of this complex structure or restricted complex structure encodes essentially all information about correlations and entanglement. Yes? You mean this? So this is a linear map. So what I'm meaning is you can think of this as this is a linear map in phase space. As such, you can diagonalize it. You can diagonalize it, right? It has eigenvalues. So for this one, all the eigenvalues are plus minus y, so complex, the complex unit. For this one, you have plus minus something that is strictly larger than unity. Those numbers are called symplectic eigenvalues and characterize your essentially your map.
I'm trying to understand what is this inequality. It's a condition on the eigen.
Yeah.
Close.
Yes.
I was just trying to understand what's the meaning of this inequality. If I want to understand, it's a condition on the eigenvalues.
Exactly, it's a condition on this map. And you can define actually what it means to have a mixed Gaussian state or a pure Gaussian state by the eigenvalues of this map. Yes. Sorry, I didn't hear you.
So does this define what you mean by a mixed Gaussian state?
Actually, yes, it is one. You can define mixed Gaussian states like this. Perhaps the definition that you have in mind from quantum mechanics is Pure state is a state that I can represent as a vector in my Hilbert space. Mixed state is a probabilistic mixture of pure states, but you can show that for Gaussian states, the characterization is equivalent to this one in terms of this complex structure. Yes. Okay, any more questions? No? Okay, so let me quickly finish by telling you that all this is really nice. I'm just not doing much. I'm just describing what is the geometry behind these simple systems. But now, if we want to go a step further, we want to understand how entanglement is distributed, then we need something else. And the kind of question I want to answer is the following. So consider, for example, quantum mechanical system that is made of n degrees of freedom, and you divide these degrees of freedom into two groups, subsystem A and subsystem B. And now you want to answer the question, well, what in this subsystem is entangled with this one? So in this case, for example, it could be a linear combination of two of these degrees of freedom. Now, this can be answered using the concept of partner modes or partner systems, which essentially is defined as the subsystem that encodes all correlations or entanglement with A. Now, this concept has been proposed, first of all, in the context of Hawking radiation by Wall in 1975, and then later on in more recent works. But the important point here is that using this geometric language, then we can rephrase and prove the existence and uniqueness of this partner system for pure Gaussian states, and we can show that it's actually completely determined from J, or well said, if this subsystem has correlations with this one, then the action of J on this, on this subsystem does not leave the subsystem invariant, and then projecting outside of this gives you exactly what this is correlated with. This is very quickly. If someone wants to know more details, I will give you after the talk. But also this language is interesting because it allows us to define what it means to have a partner system for Gaussian, mixed Gaussian states, where we find that, well, we have to make a distinction between entanglement and correlation partners, which unfortunately I don't have time to talk about today. Okay, so I hope that you are still awake, and if so, I'm going to talk about two interesting applications. The first one has to do with entanglement generation during inflation, and the second has to do with a proposal to prove this vacuum entanglement in the lab. Okay, so entanglement generation during inflation, as many of you might have heard, we believe that when our universe was very young, it underwent a period of accelerated expansion known as inflation. And this is interesting, among other things, because we think that the quantum fluctuations of certain fields during this epoch created the primordial inhomogeneities that gave later on rise to all the structure in our universe. But here, this picture is amazing, it's really nice conceptually, but we run into problems, because if we ask our friends in the cosmology department next door, they will tell us, well, when we are dealing with doing cosmological models, what we do is we replace the quantum state of cosmological perturbations at the end of inflation by a classical probability distribution. And essentially, we destroy everything that is quantum in here. And surprisingly, this works very well to explain observations, in particular, the cosmic microwave background spectrum, right? So what's going on? Do we need a quantum to classical transition or not? This is, this apparent tension is a quite well-known problem in physics. I'm not going to talk too much. Well, I'm not going to claim that I solve it, but I'm going to tell you that if you analyze exactly what are the correlations and what is the entanglement that you are producing, you can alleviate this tension up to some point. So to do this, I'm going to use a toy model, that's the Sitter spacetime, in particular the cosmological patch. So for those of you who do general relativity, this is a Penrose diagram of the Sitter universe, and I'm only taking half of it, which corresponds essentially to an expanding universe. Universe that expands with acceleration. This eta here is called the cosmological time, and this would be the metric of my spacetime. Now what I'm going to do, again, I'm working in the canonical formulation, so I take a space, a flat space, and I'm going to consider a scalar field in the Sitter spacetime in the Vance-Davis vacuum, which is let's say, the closest thing you have to Minkowski vacuum in the zeta space. Then I'm going to do as I was doing before. So I'm going to extract a single degree of freedom. In this case, for this talk, I'm going to do a special one because it's easier for what I'm going to show. So just consider a single degree of freedom that's a smeared field and a smeared momentum. I'm going to assume that these two satisfy canonical commutation relations, and therefore the algebra generated by this thing defines a single mode subsystem of my field. I can play this game again and do it with 2 degrees of freedom. And then I'm going to try to answer 2 questions. The first one is, what is the entanglement between a single degree of freedom of this form and all the infinitely many degrees of freedom of my quantum field? The second question I'm going to answer is, given 2 space-like separated localized observables, what is the entanglement between them? To answer the first question, I'm going to use this concept or this construction of partner systems. In this case, I'm going to use a basis simply because for representation is useful. And then what I'm going to try to do is find such functions that define a single mode subsystem such that this purifies my original degree of freedom. For concreteness, I'm choosing these profiles for the functions f and g that generate this degree of freedom. And if I compute the partner system in flat spacetime, what I find, first of all, quite surprisingly, is that the partner system of any compactly supported degree of freedom is not of compact support. In fact, it has a specific decay that does not depend on the details of what I have here. In that sense, this is universal. What I find in the zeta spacetime is even more surprising because, more or less same thing. But now what I find is that the decay of this partner system is considerably much lower than it is in Minkowski spacetime. And what this is telling me is that entanglement in the zeta spacetime is spread out at very long distances, in particular outside the Hubble radius. Now, what happens with entanglement between 2 degrees of freedom? I'm not going to tell you many details of this, but we can try to compute it using entanglement measures. Yes? Yes.
In flat spacetime, you could look at 2 Rindler wedges as well.
Yes.
And do you have similar behavior for
Yes.
Rindler wedges?
So basically, depends if you take modes that are localized in your right Rindler wedge, and if you take a mode that is localized in the right Rindler wedge, you are going to find that its partner extends to the left Rindler wedge. So you have correlations between the 2 Rindler wedges. Yes, so in that sense, yes. Yes, exactly. You can apply these techniques also in this situation. Now, if I want to answer what is the entanglement between these 2 things, what I'm going to find is I can quantify this, for example, using something called logarithmic negativity. That's not very important. What's important is that I can find a term, that is dominating, well, I'm calling it Minkowski, that dominates when the 2 modes are very, very small and they are close to each other, and some additional contributions. These additional contributions are functions that are complicated, depend essentially on the size of these things, depend on the distance between them, depend on these functions. But the important point is using techniques of functional analysis, we can bound this contribution. And we find that it's always negative. Or in other words, we find that entanglement with the partner, which is spread out at very long distances, acts as noise for local observables. And therefore, inflation is not creating entanglement between local observables at all. This obviously has implications for cosmology. As I mentioned earlier, we have this period of accelerated expansion called inflation. And it is a question, well, if what we have here has quantum origin, how come that we don't see any of this quantum origin anywhere else? And while I'm not claiming to solve the complete problem because it's very complicated, you can consider the coherence, you can consider many, many things that happen. Plus, we don't really have access to everything that happens beyond this deformation of the CMB. If inflation does not generate entanglement between those observables that we can access in the first place, then this question is not so relevant after all. Well, probably that's also up for discussion. Leave it for the question session. But I hope that I could convince you that in order to really try to understand this problem, we should focus on those things, on those observables that we could potentially observe. And that means things that are localized within our universe. And when we do that, then we observe that the generation of entanglement, well, it doesn't happen at all in the first place. So this is the first application I wanted to mention. But you know, this is still a bit abstract, still perhaps not so interesting to many of you because, well, who cares? It's not like perhaps we can, you know, do quantum tomography of the CMB in the first place. So yeah, is there something more tangible that we can do with these techniques? And the answer is, well, I hope so. So in the past few years, one of the things that I've been doing with some collaborators is trying to understand what aspects of this rich entanglement structure of the vacuum survive in these finite dimensional systems. And we've come to several kind of, you know, interesting results. For example, we know that it becomes sparser in increasing spatial dimensions. We know that entanglement, even though it is very much sparse between two-mode systems, is actually quite generic in multi-mode subsystems. We know that it's affected by space-time curvature. But okay, at least we believe we know. We have theoretical results, but can we test any of this? And well, I'm not going to say that we can't because technically we haven't done it yet, but I'm saying, well, perhaps we have some hope to do it. And the reason we have hope to do it is because now we can use quantum fluid simulators. In particular, a whole field that is called analog gravity offers, let's say, possibility to actually test these things. For those of you who have not heard of quantum gravity, it's a field that explores analogs of general relativistic gravitational fields within other physical systems. It was suggested first by Unruh by pointing out that, well, if you look at a waterfall and fish is trying to, you know, climb the waterfall, this can be an analog model of a black hole, in the sense that also you have a point of no return where the fishes are just going to go down and probably die, poor things. But you know, this is still a bit hand-wavy, and I can see some of you in the audience kind of cringing at the thought. But actually, there is a theorem, so we can make this precise, I'm sorry, which tell us that sound waves in inviscid barotropic rotational fluids actually satisfied a Klein-Gordon equation in a core background. So we can make this precise. We can give some content, mathematical context to these statements. And and using this, we can, some people, not me, can simulate black holes, expanding universes, ergoid regions, and other physically interesting things. Now, what I'm going to talk about is a very interesting kind of system, which is given by Bose-Einstein condensates. Do you have a question? It says 7 here. Okay, I'll try to rush. So these are very loosely speaking, quantum systems where we cool down atoms so much that they condense into the same lowest possible energy state, and they behave as a quantum entity. And in fact, what we can show is that linearized collective excitations in these Bose-Einstein condensates satisfy an equation that is very similar to the Klein-Gordon equation. I can tell you later why it's not exactly the Klein-Gordon, where this thing here is called the healing length, and this thing is the speed of sound of these collective excitations in the Bose-Einstein condensate. Now, it turns out that in the so-called relativistic limit, so when this thing is small compared to this one, then we can show that the collective linear excitations in BCs behave as a scalar field and, well, in a thermal state. So, very good. Let's see what we can do with this. So do we have existing experimental platforms that we can use to exploit this? The answer is yes. There are already some existing experimental platforms to try to test these properties. In particular, I'm going to focus on this one given by these wonderful people, where Alvaro is one of my collaborators. And this allows us to test things in 1+2 dimensional Bose-Einstein condensates. Importantly, this particular realization allows us to perform quantum state tomography, so we can reconstruct essentially the covariance matrix of the whole Gaussian state of the system, and they can reach temperatures of up to 10 nanokelvin. This is extremely low, and it is important because the thing is, up to now, we didn't have access experimentally to anything that happens in the vacuum because thermal excitations, thermal noise is too high. But now we are entering a regime where actually, if you look, this is the thermal contribution, well, ratio of thermal contribution respect to vacuum contributions, and you are seeing that, well, this is essentially of order unity. So for the first time, we are entering into a regime where we can hope to test some of the vacuum expectation, well, some of the vacuum properties. Now, so what you will have in this case is, as I was mentioning, kind of a blur reconstruction of this VC. You can reconstruct the quantum state of this thing, but you do it in pixels. So this is kind of a density contrast. But this is a representation. It's based on their, yeah. But the point is, this density contrast is related to the 2-point function. So essentially, basically, this allows you to reconstruct, well, this plus the time derivative allows you to reconstruct the full quantum state. Yeah, so when I'm plotting this is just to make the point that, well, we can use these smeared observables also in this context, in the sense that trying to measure entanglement between any 2 pixels of this condensate is just not possible. There's too much noise. It is something small. There is not enough entanglement. But if we create, let's say, collective degrees of freedom based on summing up weights of all these pixels that fall into here with a certain weight that I'm approximating with this function, and add another one, and another one, and another one, and compute the entanglement between the systems that are in each of the, well, between the red ones and these ones, then we have the hope to actually measure entanglement. And this is what we are seeing. So basically here I'm plotting entanglement, more concretely logarithmic negativity, in this kind of collective degrees of freedom as a function of temperature in nanokelvin. And what we see is that around 10 nanokelvin, we still have entanglement between these collective degrees of freedom, at least when we add enough layers. So basically enough degrees of freedom in this configuration. Now this is not enough because, in this calculation, I'm assuming that everything is perfect, but, well, we have experimental errors. So we try to check a model of experimental errors, and what we find is that if we assume a 5% relative errors, which is what was reported in the experiment that we are trying to model this effect after, then we can detect entanglement a little bit below 10 nanokelvin with a certainty of 99.7%. So this is still work in progress, but what I want to convince you about is that quantum fluid platforms are promising as pros for quantum vacuum entanglement. So this is extremely exciting. Let me summarize and give you some of the conclusions, and I'm going to finish very quickly. So quantum vacuum, the vacuum of a quantum field theory has a surprisingly rich entanglement structure. But we know this, but this is not enough. As physicists, we want to answer concrete questions. For example, how is this entanglement distributed? And what part of this entanglement can we access? So in order to try to give some, clarity into these questions, I've talked about partner systems, so how that model how this entanglement is distributed. And I have told you that the story changes quite a bit if you focus on the entanglement between finite number of degrees of freedom. And using these techniques, I have tried to give you 2 interesting applications. The first one on entanglement generation during inflation, where we have seen that the entanglement with the partner in the Sitter spacetime spreads over large distances, which essentially means that this entanglement spread out long distances acts as noise for local observables, and therefore inflation does not create entanglement between those observables that we can hope to access. Now, I have also given you a proposal to prove QFT vacuum entanglement. And this is still only theoretical work. But what I can tell you is that I'm quite excited about this, because right now we are finally being able to probe those extremely low temperatures that we need in order to make this even feasible. And then with this very simple example, I want to try to convince you, or I hope I convince you, that these quantum fluid platforms are promising probes for this QFT vacuum entanglement. So thank you very much for your attention.
Thank you very much, Patricia. Are there questions, comments? Yes, please.
Just clarify how you got a type 1 algebra by some truncation that you did.
Sorry, can you speak a bit louder? I don't hear you.
How are you able to get type 1 algebra starting with local QFT?
Yes, so basically, this is a result of this smearing. When you get this smearing, I'm getting essentially operators of the quantum field theory. These operators are normalizable, basically, so you can compute expectation. Oh, no, okay. You can compute vacuum expectation values of these. These are finite. And then, you can create algebra by taking products and linear combinations of these things. And yeah, they are type 1. This is, if you want the intuitive reason why these are type 1 and not type 3 is one of the reasons you have all the complications in type 3 is of these infinitely many degrees of freedom and the correlations that exist between them, right? So if you take a region, all the degrees of freedom of a region and its complement, and you have a Hadamard state, what happens is that you have correlations that are infinitely close to the boundary. This is the physical way in which I understand this. But now, if you only have 1 degree of freedom that you are taking out of this one, then this problem is not there anymore. You are cutting the correlations, if you want, all these infinity correlations by taking just one thing or 1 degree of freedom. And you can repeat the process up to n, with n arbitrarily large, but finite.
Yeah, that's what is not clear to me. Even if we smear it locally, it doesn't truncate to 1 degree of freedom, right?
It is. This is how I'm defining. Let me give you, Yes, so maybe, let me give you an example.
UV cutoff involved in some way.
Sorry?
Is there a UV cutoff involved in some way?
So the UV cutoff is essentially inbuilt in these smearing functions. So these ones don't have infinitely, they don't have infinitely fine features. So there is the UV cutoff in some way.
Okay, so these are not smooth compact functions.
These are smooth compact functions, yes.
So then it will have, I don't see where is the cutoff.
It's inbuilt in these functions. Let me give you an example. In this case, these functions are not smooth. They are finally differentiable. You can show that this is okay. Basically, there are a lot of details that I have not discussed here. But when we are working, when we are constructed the Fock space of our theory, we have to essentially enlarge, we are choosing a norm or an inner product in our phase space. We are using this to Cauchy complete our phase space. Then we are complexifying it and we are splitting it to create the one particle Hilbert space. So in this process of Cauchy completion, we are enlarging our phase space. So what I call usually the enlarged Cauchy completed phase space of your theory. And this contains things that are not necessarily smooth and not necessarily of compact support. This is also one of the reasons why the partner of something that is of compact support is not of compact support. So essentially, as an example, just take these two initial data. With these two things, you can generate, you can generate a single degree of freedom, and you can take functions that are of this form. Then you can do things, essentially everything analytic, and you see that whatever you obtain is finite. You don't get any divergences. The UV cutoff, again, is inbuilt in the structure of these functions. So, for example, you see here, you get these two smeared operators that depend on this parameter delta. Then you can compute the reduced symplectic form. This is the Minkowski vacuum, so you have see nothing here. And you can compute the reduced covariance matrix for this system, which can be given in terms of Sobolev products, Sobolev inner products, which I have defined here. And yeah, this thing is finite. In fact, you can compute it exactly in terms of gamma functions. So yeah, there's this you have extracted a single degree of freedom of your field, and it is a finite algebra. This is a quantum mechanical degree of freedom, if you want. I know that it's a bit surprising. I was also surprised, I have to admit.
Maybe you can pursue this
Yeah.
discussion during the break. Are there more questions? Yes. So,
Uh, Maybe it's like quite a naive question, but then right now we're just like doing massless scalar fields, right?
Yes.
But then like, have you like considered maybe like more types of fields, like fermions and everything, like how things would change? Since like you said that we would like look at like Bose-Einstein condensate, and that would require fermions to come into the picture somehow, right?
Okay, it's actually a very good question what you are asking. So thank you very much for it. I have to say, what I've shown is true, is mostly for essentially massless fields, massless bosonic fields. You can treat in the same language of these scalar spaces free bosonic, free fermionic systems in Gaussian states. In that case, what you see is that what you have given, if you want, is a metric in phase space, and then the anti-symmetric structure depends on the state of the fermion system. So those you can treat. Again, it's only, this formalism is limited to free theories. So we cannot really deal with interactions and for Gaussian states. And when it comes to massive fields, I have done some work with them. The thing is that the moment you add a mass, it works against entanglement. So I'm interested in this kind of correlation in this resource. So I usually am more interested in going towards fields that are very light or massless.
The mass acts like a regulator type of thing, which regulates the entanglement.
The mass, yeah, the presence of a mass essentially acts in detriment of the entanglement content. In fact, yeah, it also decreases the correlations at long distances. Well, that's one of the reasons why.
Okay. Thank you.
So there's this work in cosmology which is about decoherence, which is the
Yes.
transition from quantum to classical. So I was wondering if your result about entanglement like changes this result in any way?
So the thing is, it doesn't change it. It's simply, I think it complements it, right? So basically, I'm not saying that, again, I'm not saying I'm solving anything. I'm just saying this is a very complicated problem. It has many phases to it. One of them can be the effect of the coherence. I'm not dealing with the coherence. This is too complicated for me. What I'm saying is, if you don't generate entanglement in the first place, actually entanglement is, generation of entanglement between these localized observables is very, very much suppressed. Then, you add another layer to it, which means potential decoherence, but you don't have a lot of entanglement to begin with. So it's perhaps less of a problem. In fact, just to give you some numbers, and I hope that, I'm not going to embarrass myself with this. So if you look at, let's say, the pixels of what you can observe in the CMB, the smallest kind of precision that you can get, what you realize is that if you would backtrack it towards inflation, then you will have something that is of the order of 10 to the 60 times the Hubble radius at that time. And what I'm finding is that essentially the size of these pixels is huge, and then the entanglement between these is very much suppressed because the suppression is a polynomial factor of the size of these pixels in units of the Hubble radius.
Okay, I have a very naive question, because in one of your slides,
Yes.
you wrote entanglement partners and correlated partners. Do I understand them correctly, that one belongs to the quantum world and one to the classical world?
So more or less, so basically in quantum systems, we have entanglement, but entanglement is only a subset of the correlations you can have. You can also have other types of correlations, which I'm calling other things. These correlation partners are measuring everything. So they are measuring all types of correlations. Entanglement partners are restricting view to just try to identify what entanglement is in these systems. And they have very interesting properties. So for example, correlation partners in Even in these subsystems, they are correspond to infinite dimensional subspaces. We just tell you that even a single degree of freedom of your field is correlated with everything else or with many things, infinitely many things. But it's only entangled if you have only 1 degree of freedom and you're looking at a subsystem with 1 degree of freedom, its entanglement partner is also one-dimensional. So essentially, well, it corresponds to another degree of freedom. So entanglement is a very small subset in that sense of all the kind of correlations you can have.
So the second question, sorry, it's what it is thermal state?
What is a thermal state?
Thermal state. Sorry,
No worries.
I don't know what it is.
Well, now it's my turn to embarrass myself, perhaps. Let's just say when I'm talking about Gaussian states include vacuum states that we are perhaps more used to, but it also includes other states, right? They include squeeze states, they include these thermal states that you're asking about, it includes coherent states. So all of these states can be treated under this kind of framework. And thermal states, if you want, they are states at a given thermal equilibrium. So in this case, they are characterized, in this language, they are very easily characterized with an additional term that is basically the thermal occupation number.
So I think there would be many more questions and discussions, but we'll leave that for the break. Thank you very much, Patricia. And I suggest, if the chief agrees, to resume at 20 past. Is that okay? 20 past. 20 past.